In this video, I am going to cover the second half of chapter 6.2. And in this lesson, we're going to look at how to use that standard reduction potential table to predict redox reactions, whether they will occur or will be non-spontaneous or what's going to happen there. We'll also look at redox titrations in this lesson as well. So there are a few goals for this. We're going to classify the strength of oxidation and reducing agents based on their position on the table. We'll define what the reduction potential is, that's E naught, that is listed on the table with it. We'll predict predominant reactions based on that table. And then finally, we're going to look at some redox titrations to determine a chemical's concentration. So when we're looking at oxidizing and reducing agents, what we're really looking at is transfer of electrons. How electrons are transferred from one agent, or I should say from one particular species to another. And if a chemical is good at donating an electron, it's not going to be good at accepting electron. This is very similar to what we talked about in acid-base chemistry about how if a chemical is good at donating a proton, it's not going to be so good at accepting one. So it kind of stands to reason that the stronger the oxidizing agent is, the weaker its complementary reducing agent will be. So just as we looked at acids and bases and said that strong acids, or I should say strong weak acids, have weak conjugate bases, this is the same sort of thing. The stronger that oxidizing agent is, means that the complementary reducing agent is going to be quite weak. The way we measure the strength of the oxidizing agent is the reduction potential, and that's E naught that is listed in the chart. That shows the potential to be reduced, and that reduction potential is measured in volts. So it's measuring a potential difference over a particular region. The strength of the reducing agent is measured by the oxidation potential, so the potential to be oxidized, and it's kind of the reverse of that reduction potential. Now, the nice part about this is to find the oxidation potential. So if we're trying to look at the reaction going backwards, all we have to do with that E naught value is reverse the sign. So take it from a negative to a positive, or from a positive to a negative. It's kind of like when we were calculating KBs using the Ka table, but this time there's no really tricky math going on. All you have to do is flip the sign of that E naught. So here are a couple of example problems. If we want to find the reduction potential of Br2, well, we locate Br2 on the chart right up near the top, and we're reading that reaction going from left to right. So we're going to keep the sign the same as what it is on the chart. So that E naught is going to be positive 1.09 volts. Oxidation potential of silver, however, is reading from right to left. So we're looking at oxidation potential instead. With that one, we're going to reverse the sign. So instead of positive 0.80, we reverse that to negative 0.80. And then other questions that you could get from this, which is a stronger reducing agent? Well, we can just locate both of those on the chart. Okay, both our Sn and our Pb are found on the right-hand side of that equation there, and the stronger reducing agents are found closest to the bottom. So in this particular case, Sn is a stronger reducing agent. One other thing that we can tell from the table is what kind of predominant redox reaction will take place. With a predominant redox reaction, we are looking for the strongest oxidizing agent and the strongest reducing agent going together. So you're going to be looking for the two things on the chart that are found farthest apart when you're looking for the predominant redox reaction that's going to take place for spontaneous reactions. So here's an example problem. What is the predominant redox reaction in the mixture of Cl2, Ag+, Sn2+, and I negative? So you want to locate those on the chart and find the two that are farthest apart. So our strongest oxidizing agent is the chlorine, Cl2. Strongest reducing agent is Sn2+, okay, on the bottom kind of right-hand side of the chart. So we're going to write out those half reactions. So I've got my Cl2 plus 2 electrons gives 2 Cl negatives. Sn2 goes to Sn4 plus 2 electrons. And with my standard or my reduction potentials. I have a positive 0.36 for the chlorine reaction, negative 0.15 for that tin. And to actually calculate the full-on potential of the reaction, I'm going to add those together and I get 1.21. For the predominant reaction, I'm going to put the two half reactions together, making sure that those electrons are balanced. And I get Cl2 plus Sn2 plus yields 2 Cl minuses plus Sn4 plus. So here are some practice problems for you to try. I'm going to recommend that you pause the video, try those 4 problems, and then come back for the solutions. Okay, so here's the solution for the first problem. We're going to look for the strongest oxidizing agent, strongest reducing agent, which are those two. With problem number 2, the electrons don't balance. I've got 2 electrons coming from that reaction with the copper, 3 coming from the one with the aluminum, so I actually have to do a little bit of math there to make it even. And there's the solution. And there's the third reaction. Interestingly enough, the Cu plus is the strongest oxidizing agent, and it's also the strongest reducing agent, going to something a little different. With question number 4, we have 4 things to consider in that solution of iron 3 chloride. We've got copper, bromine, iron ions, and chloride ions. So when we look at that, the copper and the bromine are the ones that are going to react. And there's the solution. The last thing that we're going to talk about in this lesson is redox titrations. So these are very similar to an acid-base titrations, and what we're doing is performing a titration between an oxidizing agent and a reducing agent. And the indicator in this titration is a reducing agent that's a different color in its oxidized form. Permanganate ions are almost always used for redox titrations because they go from purple to colorless in that change. And that's a natural color change. You don't even need an indicator for this particular one. So here's an example of a problem. It says to titrate a 25 milliliter sample of iron 2 plus to its equivalence point, 16.7 milliliters of 0.0152 molar manganese or permanganate in acidic solution is needed. What is the concentration of iron 2 plus? So the first thing that we're going to do is, because this is a stoichiometry equation, we're going to come up with a balanced chemical equation. So there's the chemical equation for the titration. So if you need some review about how to balance a redox reaction, please go back to one of the previous videos on balancing. Step 2 is that we're going to calculate the moles of the permanganate ion that is reacted. So this is our standard solution. You can always identify that standard solution because there's 2 pieces of information about it. And in this case, we've got the molarity and we have the volume. So we're going to take the number of moles of permanganate ion, and now we're going to cross the mole bridge using that balanced chemical equation. I've got a 5-to-1 ratio between the iron ion and that manganate ion. And then the last step here is that we're going to calculate the concentration of the iron in the original sample. So that's the sample. So we've got the moles, we want to get molarity, so we're going to divide that by the volume. Here's another sample problem for you to try. So we've got potassium dichromate used to titrate a solution of iron 2 chloride. So the potassium dichromate is the indicator. And as the dichromate solution is added to the iron solution, the orange dichromate ion is reduced to green chromium ion as it oxidizes. So with this one, we've got another type of kind of indicator that is also a an oxidizing agent. And the equivalence point is evident when the orange color remains. So what we're going to do with this one is the same thing as the last. You want to balance the redox equation for this following titration. So we'll break it into the half reactions, balance those half reactions. Reminder that we're balancing the oxygens using water. We'll balance the hydrogens using hydrogen ions. And in this case, we're going to keep it an acidic solution unless it tells us otherwise. And then we're going to go through our stoichiometry. So I'm starting with my standard. I have a 0.0200 molar solution. I multiply by the volume to get the moles of that dichromate. Cross the mole bridge, 6 irons for 1 dichromate, and then divide by the volume of the iron to figure out what my final concentration of the iron ion is. The other thing that I need to do is just making sure, you can see my net ionic equation there for iron 2 chloride, making sure that I have a 1-to-1 ratio with the iron ion and the iron chloride, iron 2 chloride. And I do, so my final solution is 0.090 moles per liter. Question 2, maybe take a pause, see if you can get this answer by itself. It's giving you a balanced equation already, so you don't have to go through that step. With these titration problems, they work out exactly the same as when we were doing them in the acid-base unit and in the solubility unit. Here's a third problem. This is a little bit of an application problem, how we can use these redox titrations to our advantage. So with this one, what we're trying to do is calculate how much ethanol is in a particular sample of wine. So with this one, we can take that dichromate ion and use it as a indicator. It's also participating in that redox reaction as well, and it goes from that orange to green color. The second part of this problem is taking that concentration of the ethanol, and now we're trying to express it as a percentage of alcohol. So again, this is a stoichiometry problem that you might have seen in a grade 11 class, but it's a nice application of how we can use this. So we take our concentration of the ethanol, we can multiply by the volume, and then multiply that by the molar mass. So we can figure out how many grams of ethanol we have because we're given a density in grams per milliliters. Okay, once we have that, the grams of ethanol, if we divide that by the density, we can figure out how many milliliters of actual ethanol are in our sample, and then take the number of milliliters of ethanol divided by the size of the sample, 10 milliliters, multiply by 100% to get that percentage. So I hope this helped you to understand how our redox titrations work and strengths of oxidizing and reducing agents. Please let me know if you have any questions, and thanks for watching.